Hi everybody, and welcome to the beginning of section 16.2 on page 60 of the workbook. And this is a continuation of the discussion that we had in section 16.1 where we introduced the idea of a double integral. The concept of iterated integrals is going to give us a nice way to calculate double integrals if we have a formula for a function. Okay, so to get started with this discussion, let's look at the picture over here to the left. It's sort of visually describing this process of integration that we've been talking about. Okay, so I'm going to give this rectangle that we're looking at the name R. Notice that it's been divided up into a bunch of subrectangles, and the center point of each rectangle has been chosen. So this is kind of suggesting a middle sum approximation for the integral, which we talked about in the last section. Okay, now just to nail down a couple of the points of notation, let's start by giving names to the x values of those middle points. Okay, so maybe we could call them x1, x2, x3, and we keep going until we get to the last one of them, which I'm going to call xm. We can do the same thing with the y values in the middle. Okay, just to give them names, we'll call them y1, and we'd continue until we get to the last one, which I'll call yn. Okay, so just giving names to those points, basically. Okay, and we had a way of approximating the integral. Okay, which looked like this. So that integral is approximately equal to basically just looking at those squares one at a time and multiplying function value times the area of the square. So symbolically, we could write that down. We've seen this notation a couple of times before, like this. Okay, just going to each one of those points, taking the function value and multiplying by the area. Okay, delta x and delta y, I'm going to think of as just being the length and the width of each one of those little rectangles. Okay, so we could draw that into our diagram as well. There's delta x and there's delta y. Okay, well, here comes the new idea in this section. We can actually take this sum that we have and break it, kind of organize it into two pieces, so to speak. Okay, so I'm just going to write this and then we'll sort of talk through it together. So we can break it into a sum over j and a sum over I separately. And kind of what that's suggesting is that we sort of separate our rows from our columns. So for example, this sum in the inside over I, that's going in the x direction, so it would be referring to just picking a row and sort of summing left to right. Okay, and you can do that for all three of the rows that you have up here. And after you've done that for every row, then you can sum in the j direction times delta y, going top to bottom. And what's interesting about that way of thinking about it is that what we're looking at here in the inside looks like what we called a Riemann sum in Calculus 1. It's an ordinary Calculus 1 integral in the x direction, going left to right. And then similarly, when we're done with that sum on the inside and we're ready to sum with respect to j in the y direction, that's also a Calculus 1 integral, but in the y direction. Okay, so here's what we get if we put all that together. If we take the limit as delta x, delta y go to 0, okay, it can be shown that we've essentially taken this double integral and divided it into two separate Calculus 1 integrals. Here's how it would look. So on the inside, we'd be integrating from a to b, f of xy dx. And I want to just remind you where the a and the b are coming from in our picture, if we can sneak that in. Okay, here's a and b. And then we're going to integrate in the vertical direction from c to d, dy. That kind of corresponds to the outer sum. There's the c and the d. And there's a name for what we just wrote down. This is called an iterated integral. Okay, and it just says if we want to calculate a double integral, we can break it into two calculus 1 integrals, one in the x direction and one in the y direction. Okay, so kind of pulling this all together into one theorem, it just says that anytime we're in the situation of integrating over a rectangle, okay, provided that our function is reasonably nice over the rectangle we're integrating in, we can break it down into two calculus 1 integrals. It doesn't really matter what order we do it in. Okay, so we could either do it like this and integrate with respect to x on the inside and y on the outside, or if we wanted to, we could do it in the other order. Doesn't matter. Okay, we're going to get the same result in both cases. Okay, and in the next example, we'll see how this works to actually calculate an integral.